In this word problem, we have a garden hose and it has an unobstructed opening with an inside diameter measuring 1.9 centimeters, much like you see right here in this picture. And here's a garden hose. It's filled with water and the water is flowing out. And this flow that you see here exiting the garden hose follows the equations of continuity. And if we were to put an obstruction here, much like this, put your thumb at the end of that hose, and many have done this, and you can then see that the water streams out and it's much, much faster than the water flowing through here. Again, this follows the equations of continuity. And that's what this word problem is about, looking at these two situations here, one that is unobstructed and one with an obstruction, both of them following the equation of continuity. So let's go ahead and solve this. Here is the word problem. So a garden hose has an unobstructed opening with an inside diameter measuring 1.9 centimeters, from which water fills a bucket in 13 seconds. The volume of the bucket is 8 liters, about 2 gallons. Find the speed of the water that leaves the hose through A, the unobstructed opening, and the obstructed opening. In this video, I'm only going to do part A. In a separate video, we'll finish part B. So let's draw a picture of what is being asked. We'll draw a garden hose. Garden hose has an opening at one end attached to a spout at the house, such that water is filling in, and it has an opening at the other end. And we'll make this circular such that it flows through. And it's all the same cross section going all the way across. In this case, it is 1.9 centimeters in diameter. So the diameter of this throughout from the beginning to the end is equal to 1.9 centimeters. And we're going to use the equation of continuity to solve this problem, part A. Let's have a look at our equations. Continuity. Let's develop this equation first using equation 52. This is the equation of continuity. So let's use this at both ends of the hose and see how we can arrive at this one, equation 48. So here at the beginning, water enters the pipe or the tube, or in this case here the water hose, and it has the equation Q dot 1 is equal to the cross-sectional area times the velocity at 1. We'll call this at location 1. Q dot is the flow rate. A is the cross-sectional area right here. And the velocity of the fluid going in the tube at this point. Going through all the way to the other end, we'll call this point 2. We'll call this point 2 and call this one here point 1. And this equation can also be used at the other end. There is no changes that happen here. Therefore, Q dot 2, or the volume flow rate, is equal to the area here at 2 times the velocity at 2. Q dot 1 and Q dot 2, this is the volume flow rate, or the amount of fluid entering here has to equal the amount of fluid exiting at the other end. Since this has to equal what's coming out, therefore we can equate Q1 to Q2. Volume flow rate going in must equal the volume flow rate leaving. What comes in must come out. Since we're equating both the left-hand sides of the equation, we can then equate the right-hand side of the equation. Therefore, A1 V1 is equal to A2 V2. And this is another form of the continuity equation throughout the pipe. In this particular case, it is a uniform cross-sectional diameter. Therefore, we can just use either this equation or this one here at either end. For part B, we'll be using this one in part B for the other video. But for this video, I'm only going to concentrate on part A. So let's solve part A. Make a list of what we are given. We know the diameter, and let's look here. It says here, garden hose has an unobstructed opening Unobstructed opening, we're looking at this scenario here. And the pipe has to be filled with water. So it's completely full and water is moving out at some velocity. And we'll consider it at this end here. And water is leaving here at some velocity. So a garden hose has an unobstructed opening with an inside diameter measuring 1.9 centimeters diameter. And we'll call this diameter 2. It doesn't matter because it's the same throughout. Is equal to 1.9 centimeters. And we need to change this to proper base units. So we'll do that right here. 1 meter per 100 centimeters. And that gives us 0.019 meters. That will be the diameter at this point. And we're given some time. And a bucket is filled in 13 seconds. So time was given to us as 13 seconds. And we also have volume. The volume of the bucket is 8 liters. So we want to measure this, the volume flow rate, as 8 liters. Volume is equal to 8.0 liters. Now liters is a volume, but we won't need to change this to cubic meters. So we'll do a quick conversion right here. 1 cubic meters per 1 liter. Liters and liters will cancel out. Therefore, the volume is equal to 0.008 cubic meters. And Q dot is the volume flow rate. Q dot is the volume flow rate. And this word rate means something divided by time. It means something, and the something changes divided by time. And time can be in seconds or hours or minutes, but it means something divided by time. In our case, that something is this volume divided by time. Therefore, our Q, volume flow rate, is equal to the volume, 0.008 cubic meters divided by time. And the time we were given is 13 seconds. And we'll call this Q2 just to stay the same. We're talking about this area here. The same applies here, but we'll concentrate on this portion. And we also need an area, the cross-sectional area. Well, right down here, cross-section. At this end right here, it's a circular hose. Most hoses are circular, so this is this one. And if I were to look at the end right here, I'd see a circle. If I'm looking at the end, I would see a circle. And that circle here is filled with water. And this area represents the cross-sectional area, which is here. And the area of a circle is pi r squared. And that's what we have here. So the area is equal to pi r squared. So we have what we need now. And let's see what's being asked of us. It says, find the speed of the water that leaves the hose. So in our list of given, I always write down what we're looking for. This is velocity, little v. And I'll just completely write it down here. Velocity is equal to, we don't know. And that velocity is this v here. Utilizing this equation right here. And we're doing part A for this video. Find speed v, v2. And because this is completely linear and there's no changes in diameters, the velocity here has to equal the velocity here. Okay. But we're going to find this one, v2. So Q2 is equal to A2 velocity 2. Putting in the numbers that we have, the volume flow rate. Volume flow rate is 0.008 cubic meters over 13 seconds. And that's equal to the area, A2, which would be pi r squared. Now the radius of this, we're given a diameter of, in meters, 0.019 meters. Half of that will be the radius. So we can put in the radius here. 0.019 divided by 2 will be the radius, all squared. And that'll be in meters squared times the velocity, v2. Isolating v2. Now in your calculator, you could reduce this to cubic meters per second, just divide by 13, 0.008 divided by 13. And you could reduce this to a single number as well. But I'm going to work with what we have here and then use the calculator at the end. So we have the volume flow rate here on the left. We need to divide both sides by the area. 0.008 cubic meters per 13 seconds divided by, bring this over to the left-hand side, pi times 0.019 divided by 2 all squared, meters squared is equal to the velocity. And looking at the units, meters squared, and this is 3 cubic meters, so 2 will have 1 left over. So the units will be in meters per second, and that's what the proper units for velocity. Putting this in the calculator, 0.008 divided by 13, everything divided by what we see down here, that will give us 2.17 meters per second. And finally, reducing this to significant figures. We're given 2 significant figures here, 2 here, and 2 for the liters. Everything is in 2. So properly doing this to proper significant figures, velocity 2 is approximately equal to 2.2 meters per second. Make a correction here.